Welcome to Chemistry 111. Last class we finished thermodynamics, so we'll start by reviewing some of the homework, and then we'll start on the last chapter, which is the gas chapter, depending on how much time we have left. Reminder for those in lab, you need to be working on the online labs. Sure you get a couple of those done. I was going to say another thing was don't forget to turn in various lab reports so I can update the grade book. If you're wondering what you're missing, just come by my office. We'll figure it out together. Well, without further ado, I'm going to go ahead and get started. Start by looking at some of this. Okay. So there's only 13 questions for at least the thermodynamics, so let's take it rather easily, go through some of these. At constant pressure, which one of these would this do work on the surroundings? So looking at this, you got to remember a few things. This one, you do not have to use numbers, but you have to be able to think about it. This one's a little bit harder because we're not quite there yet. As soon as we hit the gas phase chapter, it'll make a little bit more sense. But the idea of work is created by, at a constant pressure, a volume expands. Now, an ideal gas, which is something we'll talk about next chapter, we treat all gases as identical. And so a volume ends up being proportional to the number of gas molecules. So if we treat all gas molecules the same, and a volume is proportional to the molecules, more molecules means larger volume. So to answer the question, which one of these would do work on the surroundings, you're looking at which one of these scenarios do the amount of gas molecules increase. So scenario 1, we have 2 moles of A, 1 mole of B, so a total of 3 moles of gas goes to 1 mole of gas. 3 goes to 1, we see a decrease. 1A, 2B goes to 2C. 3 to 2, still a decrease. 2 moles of A of gas, 1 mole of B of solid, 3 moles of C of gas. Because of the nature, solids don't take up much room. The only thing that will matter is the expansion of gases. So 2 moles of gas to 3 moles of gas would be an increase. An increase in gases means an increase in volume, and thus an increase in work. 2 moles of gas goes to 3 moles of gas. Once again, an increase. Your scenarios may be completely different. So take a look at your own numbers. Don't just click the bottom 2. Now in this one, a system does 526 kilojoules of work and loses 251 kilojoules of heat. So does work, loses heat. They want to know what is the change in internal energy. Sometimes it's delta U, sometimes it's delta E, but it's the same thing. The whole idea here is I don't really even need to go to the doc-cam, but I will for our sake. So 526, the delta U is equal to heat plus work. We say we did work and we lost heat. And so our scenario here is delta U equals negative heat and plus a negative work. Work is leaving the system, heat is leaving the system, so they're both negative. You add these together, you would get, simply, like negative 777. Well, that's convenient. So don't look, if I put one just like this on the test, don't look a gift horse in the mouth. All you have to do for something like this is to figure out the signs. The hard part is that I'm not going to necessarily just scream out negative, but the fact when it leaves the system and goes to the surroundings, it's negative. When it enters the system from the surroundings, it's positive. Okay. For this one, you will have to do the interactive. I'm going to leave it in there. But basically, I think you put the solution in and you see, does the temperature go down or the temperature go up? Does the solution get colder? Does the solution get hotter? And remember, endothermic means absorbing heat. Exothermic means releasing heat. So if I can't remember what the interactive is like without clicking on it, but if you're putting this into a liquid and the liquid temperature decreases, the solution has donated heat to the system, which is the reaction. So, okay, here's a calorimetry problem. Calorimetry, writing what I know now, the mass. 51.53 grams a sample, initially at 20.7. After absorbing heat of 1947 joules, the temperature is 11.7. And they want to know, what is the heat capacity? What is the specific heat capacity? So this is just a rearrangement of an equation. This is why we ask you to go through pre-calc so that you can understand that this equation, Q equals MC delta T. So rearranging that Q into MC TF minus TI, we are solving for our capital C. So we're going to take our Q, which is 1947 joules, and divide by our mass, which is 5153, and our delta T, which is the difference between 111.7 and 20.7. Do that math real quick. That's what, 91? 91.0. So our C is 1947. We have to make sure order of operation, so divide by 5153, then divide by 91, and would get our answer as 0.415. Or maybe 4152, depending on how many sig figs you go out to. But that is just a simple rearrangement of that equation. Okay. Oh, yeah, I gotta pull that up. That would be why. Point 415. Maybe do one more of these. Let's look at, see what the next couple problems are. So this one, okay. This one, they give us the information. Here's our change in temperature. Here's our mass. Here's our heat flow. we are to find the specific heat capacity and determine which of these substances it is. So pretty much the exact same steps, except now we must match the specific heat capacity to one of these values on the table. I'm going to go ahead and skip this one because it's literally the exact same process. Except now you've got, you have a set amount of choices. Is it aluminum with a really high heat capacity? Is it lead with a really low heat capacity? Is it somewhere in the middle? You can determine what is your substance by looking at the heat capacity. And this one, cooking oil has a heat capacity of 1.75 joules per gram Celsius. How much energy is needed to raise 2.81 kilograms of oil? I'm not going to fully solve this one, but I'll start to set it up. Q equals mc delta T. So C is, we say 1.75 joules per gram C. Mass is 2.81 kilograms. And temperature would be from 23 to 191. So without really setting this up, without really solving this, delta T is straightforward. Delta T is going to be our 191 minus 23. It's going to be a big number. Now, the only part that will trick you is look very carefully. What are the units here? This is joule, gram, Celsius. This is Celsius. So this, whatever this number is, it's going to give us Celsius. But what is this? This is kilograms. This is not 2.81 grams. This is 2.81 kilograms. So in order to do this math, we need to convert kilograms to grams. So you just have to remember 2.81 kilograms. There is, in 1 kilogram, 1,000 grams. Doing that conversion, we at that point have our mass, we have our delta T, we have our C, we plug those in, multiply, and you will get your heat capacity, your heat change. So don't overthink this one. There is a trick to it, but it's not a big trick. It's, if you're looking very carefully, it's pretty obvious. But I'm going ahead and spouting it out so that you kind of take a look for it. Let's see with this one. Okay, this one, once again, I might not do this one, but so what is the issue here? The issue here is that they give you the heat capacity, the mass, and the heat flow, Q. And they are asking for the final temperature. Rearranging your equation, you can find the change in temperature. But then we have to do one more step. Because they asked for the final temperature given the initial. So that you would rearrange this, Q equals mc delta T, to get Q over m times C equals delta T. You'll get some number. But you remember, that is not your answer. That is what you're solving for initially, but your final answer would be if delta T it's equal to TF minus TI. So to get TF, we can say delta T plus TI equals TF. So once you get the delta T, you can add 20 degrees onto it. and get your TF. Please keep in mind, your final temperature may not be 20 degrees. Your final temperature may be, your initial temperature may be 25. Just make sure you use the numbers for your problem. But, okay, I just wanted to start setting some of these up. We'll go ahead and do this one. So here, where this guy differs is it doesn't ask for the joules or joules per gram or heat capacity. It is asking you for the molar heat of solution. The molar heat of solution, we say 7 grams of KSCN, potassium thiocyanate, is dissolved in a calorimeter that has a total heat capacity. So the heat capacity of this is 4.47. Note it's kilojoules per Kelvin. It doesn't, this guy doesn't take into account mass. This doesn't take into account the mass. And the temperature decreases by 0.390 Kelvin. And then finally, they ask, what is the molar heat capacity in kilojoules per mole? Now, this one has 2 little tricks in there, and I'm going to go ahead and we'll actually solve this guy because this takes it 2 more steps. The idea here is that Q of reaction is going to equal negative Q of the calorimeter. The idea that whatever the reaction produces is absorbed by the calorimeter. Whatever the reaction produces is absorbed by the calorimeter. So we have a negative sign. Now the calorimeter is described by C delta T. There's our C, there's our delta T. So we're saying that the Q of reaction is equal to negative C delta T. And that's going to equal to the Q of reaction. Now, we said the heat capacity of the calorimeter is 4.47 kilojoules per Kelvin. We are told in the problem that the temperature of the calorimeter goes down by 0.39 Kelvin. So delta T is negative 0.39 Kelvin. Doing all this together, negative this times negative that would give a positive number. 4.47 times 0.39 gives us 1.7433 kilojoules. Now that gives us an energy, a straight up energy. However, this is not my final answer. What is the final answer need to be in? Kilojoules per mole. We have to watch out. This is a straight up, what's it, like extensive number that we're looking at. This is the actual number we read. However, we're looking for an intensive ratio, a ratio that will tell us this will be the same per mole no matter what. We used 7 grams. What would happen if we used 1 gram? Well, we'd have less of a change. If we used 18 grams, would have more of a change. So what do we have to do to turn kilojoules into kilojoules per mole? We have to divide by the moles of KSCN dissolved. To get the moles of KSCN dissolved, we're going to have to use our mass and the molar mass of KSCN. So we have 7.0 grams of KSCN. CN. And let's look at what is the molar mass. We have to calculate it, KSCN. K, if I'm not mistaken, is 39, but we'll double check that. 39. Hooray. K is 39. S, you look up on the table, is actually double that of oxygen, so 32. C is 12. And N is 14. Don't worry if you're still looking them up on the table. Knowing these numbers comes with an abundance of practice. And it doesn't matter if you practiced or not, because you'll always have a table. It just allows me to speed along a little bit faster. So 7 grams at a rate of 97 grams per 1 mole. So how many moles did we have? We had 0.07216 moles. So taking our original number, 1.74, we're going to divide that by our 0.07216 moles. 433 divided by 0.07216 will give us the energy as 24.16 kilojoules per mole. 24.16 kilojoules per mole. Let's try that. And the sign will matter. The sign will matter. So if it said the temperature increased by 0.39 instead of decreased, that means we would have a negative delta H. But because the temperature decreased, it is a absorption. The energy is absorbed. So that one was rather tricky. This one, another one that might be a little tricky, so we'll look at it. 2.245 gram sample of organic material. So at least we'll start setting up. Mass of 2.245 gram of organic compound is burned in a calorimeter. The temperature goes from 25.83 to 32. 25.83. And the heat capacity calorimeter is 35.13 kilojoules per degree C. What is the heat of combustion per gram? So we're looking at delta H of combustion as kilojoules per gram. Now, I'm actually not going to fully solve this one. I'm going to go ahead and set it up, and we'll look at this a bit. This one is almost identical to the last one, except for in some ways it's actually easier. The same thing, Q of reaction is going to equal to negative Q of calorimeter. Q of calorimeter is going to be negative. We're going to have our C and our, let's go ahead and calculate our delta T. 32 minus 25.83, 6.17. C times 6.17. Now this will give us an answer in kilojoules. Now, because this is a positive number and this is a positive number and we're taking this to a negative, our heat of reaction, Q reaction, will be a negative number, whatever that number is. It will be negative. Then finally, unlike the last one, we had to calculate the moles of a known substance. Now, this is an unknown organic compound with this mass. So to get this answer, we're going to take whatever number we got here divided by our 2.245 grams. And that will give us the delta H of combustion. And that will give us our answer. So you still have to work it through. But if we watch our units very carefully and pay attention to what's going on, we can make this work. You got to remember, the heat absorbed by the calorimeter or released by the calorimeter came from the reaction, so it's going to be the opposite sign of the reaction of these situations. So in this case, you should have a negative enthalpy instead of a positive one like we had last time. Okay. When 0.653 sodium is added to excess hydrochloric acid, 6790 joules of heat are produced. Okay. What they want you to do here is just convert a extensive property to an intensive property. Not too hard, but it's kind of a little confusing what they're asking for. So 2 NaCl and H2. If 0.653 grams of Na gives you 6790 joules, they're wanting to know 2 moles would give you how many kilojoules. I'm going to go into the dot cam real quick. They're saying if 0.653 grams of sodium gives me this much heat, this reaction asks for 2 moles of sodium, reacts with 2 moles of acid. So you have to figure out, you have to turn this into moles. You have to turn sodium into moles of sodium. Then you're going to say this heat divided by your moles of sodium. That's going to give you partially intensive ratio. From here, then because we're scaling it up for 2, we then multiply this by 2 moles of sodium, and that would give us our number. But for this to work, you have to figure out how many moles of sodium is this. It's going to be a really small number. It's going to be a really small number. Because molar mass of sodium is what? 23 grams per mole. And we don't even have 1 gram. Okay. Just want to look at, trying to get some of this done. Hess's law. I'll come back to that one. Thermodynamic one and thermodynamic one. Okay, so these are the ones where we're starting to get a little bit tricksy. But this is the other side of this reaction. Hess's law states whatever we have to do to combine these 2 equations to get the third, we're going to do that to our delta H values. I'm writing these down, negative 581.5 and 406.1. Your numbers may be something completely different. 2. Okay. So in one way or another, we're going to have to add these equations together. We want to get this equation. So when I do this, I typically look to see where each element is and how they match. The extra stuff, I typically don't worry about. If I've done this right, the extra stuff will cancel out. But the stuff that appears in the final equation should be there. So looking here, I see x and 1/2 O2. X and 1/2 O2 are only in equation 1. They're on the left side of equation 1. So equation 1 will be used as given. How many times do I have to use equation 1? Well, I only have to use equation 1 one time because there's 1x, 1x. 1/2 O2, 1/2 O2. Now, looking at CO2 is only in equation 2 on the right side. XCO3 is only on equation 2 on the left side. They are in the opposite sides. So what have I got to do to switch these around? I have to reverse them. I have to reverse them. So when I've done this, I've done this. X plus 1/2 O2. And I'm going to treat that arrow as an equal sign. And that's XO plus CO2. And everything on the left gets added up. Everything on the right gets added up. When I add them all up, I get X plus 1/2 O2 plus CO2 plus XO equal what yields XO plus XCO3. Now, everything that is identical left and right gets canceled out. We have an XO on the left. We have an XO on the right. XO, XO both get canceled out. The final equation reads X plus 1/2 O2 CO plus CO2 gives you XCO3. Now, so I flipped equation 2, and then I added these together. So what am I going to do? I flipped equation 2, and I added them together. So flipping equation 2 and adding it to equation 1 means I have 581.5 plus negative 406.1. Because equation 2 was positive. When I flip it, it becomes negative. So I would add those together. So you get negative 987.6. So this one was meant to be an easy Hess's law problem, as opposed to, say, some of the ones that were in the class. But if you don't understand Hess's law at all, this is still incredibly difficult. So we have to go through this. And we'll do just, well, we'll do like maybe these two. Heat of combustion for ethane. Heat of combustion for ethane in kilojoules per mole of ethane. C2, you might have to write and balance an equation. C2H6 plus O2, or we might be fortunate and be able to find it on the table. So it goes to CO2 and H2O. Let's see, balancing this to 3, 7. Let's look at this table. On a test, you will be given the relevant parts of this table. And so this table has a lot more values than we will ever need, so we're going to only use the values. So typically, on a table like this, this semester, we will only use that first column, that delta H of formation. Delta H of formation. I just want to look and see. Okay. Unfortunately, they did not give us the value, so we have to look up ethane. C2H6. Or do they not have it? Let's see. No, here it is. C2H6 is -84. Oxygen is 0. I have to go for water. Where's water? And CO2. This is really stupid. -393, 5, and let's see, 241.8. Okay. Now, if we look at the hint, thereby writing for the combustion, a hydrocarbon is stirred with reacts with oxygen in gas form. Oh, so they want us to form it liquid water. They want gaseous carbon, liquid water. So that's why I wrote down the other number, 250. They want to know what is the energy per 1 mole of ethane. 1 mole of ethane. So go into the doc cam. I conveniently, well, the equation for 1 mole of ethane. 1 mole of ethane plus 7/2 moles of oxygen produces 2 moles of CO2 and 3 moles of water. I had to balance this, 2 carbons, 6 hydrogens, 3 times 2, 6. Now, fortunately, oxygen is 0. Normally, I would say bad, very bad to put a fraction, but because they want to do it per 1 mole of ethane, it's going to make it easier to leave this as a 1. To find our delta H, we are going to say products minus reactants, the sum of products. So we have 2 CO2s, 393.5 times 2, and 2 and 3 waters, 285.8 times 3, minus 1 ethanol and 7 halves oxygen. But because oxygen is 0, it's just 1 ethanol. So adding up all the things on the left, all of the products essentially would have -1644.4, and we have on the right 84. So we add our 84 to that. Your answer is 1560.4. 1560.4. Go back to the and this one, once again, sign matters. So it was -1560.4. If you try to put it in positive, you're going to be... Now this one, just the same. Just the same. You look up the values. The only difference here is water is a gas, and this is methanol as a gas. And there's 2 of them, but it's the exact same process. You would take our numbers for CO2, take our numbers for water. 2 of them, 2 CO2s, 4 molecules of water, and 2 molecules of methanol. Products minus reactants will give you the delta H for this reaction. The exact same math. Exact same math. But that is the last problem of this assignment. So this assignment has briefly how to calculate internal energy, which is work and heat, some thoughts about internal energy and work, a lot of problems about calorimetry, and some problems about calculating delta H for reaction. So from this chapter, there would probably be a couple questions about calorimetry, a couple questions about about delta H reaction, maybe one or two about heat and work. But okay, we still have a few minutes, so we'll look a little bit of this next chapter, at least give the brief introduction. So we're at least ready. This chapter is going to be the last chapter. Not the best place to put it because we're going to talk about liquids and solids next semester, but this is a reasonably math-heavy chapter. So putting this at the end means we've had at least enough time to go through our math classes and kind of prep for this. The first thing to note is what about gases? What is a gas? What is it? A gas, while chemically different, gases are almost always very similar physically. Most gases are colorless, they're odorless. Now, almost all of them are approximately the same size on the molecular scale. This is due to the whole idea that a gas will fill a container. A solid has a definite volume, a definite shape. A liquid has a definite volume, but an indefinite shape that can slosh around very easily. A gas has both an indefinite volume and an indefinite shape because a gas will naturally expand to fill a container. So that means there's a lot of empty space within a gas. And because of that, when we're looking at atom scale, all gases are about the same size because we're looking at really, really tiny sizes. And because of this empty thing, they can expand to fill a container, but they're highly compressible. We can smoosh them together to try to fill up this empty space. And almost all gases will readily mix together because of that empty space. You can mix water vapor, which is very polar, with methane, which is very nonpolar, and they will mix without a problem. You try to bubble oil, which is very nonpolar, into water, you're not going to have that same effect because the molecules will start interacting and like push each other apart. But because of the whole nature of a gas, they don't really interact that much. So oil vapor and water vapor can mix readily. Now, looking at the origin of pressure units. We're going to have a bunch of different pressure units, and we're going to systematically try to go through these and understand where they come from. First, let's take about the generalized look of what is pressure in itself. Pressure is defined as a force applied over an area. Basically, in terms of a gas, you can look at it like a piston. There's the piston top is the area, and the gas is pushing against it. I could put pressure against a wall, pressure on a wound, whatever, by pushing down on a specific area. But when we look at pressure units, they could be ATM, which stands for atmospheres, bars, torr, millimeters of mercury, pascals, pounds per square inch, PSI. All these are just different ways of measuring pressure. We can convert them easily enough. we can convert them easily enough. There's little conversions in there. And come test time, if you do need these conversions will be given. There's never a memorize these conversions. What's the deal with all these units? Well, part of it comes to how they were kind of discovered and when they were being discovered. Now, the original unit, the scientific unit that's actually really used, the SI unit, is a Pascal, named for Blaise Pascal, Pascal's triangle. Every gas particle contains matter. So every gas particle will also contain mass. By having mass, it will be subject to gravity. Now, just because the gases float doesn't mean gravity isn't pulling down on them. It's just that the kinetic energy is greater than the effect of gravity, so they're able to bounce upwards. Now, if pressure is a force applied over an area, gravity is our force, and we're going to take a hypothetical 1 meter by 1 meter box and extend it as a giant column of air that goes into outer space. And we're going to say all the air that could fit in that 1 meter by 1 meter box, what gravimetric pressure will it be putting on the standard human being or the standard object? Well, in that box, there's about 10,000 kilograms. And gravity is 9.8 meters per second squared. So if force is a mass times acceleration, we have 10,000 kilograms times 9.8 meters per second squared. We're going to go ahead and round that to 10 for simplicity's sake. But say that, okay, that's 10 to the 5th kilograms meters per second squared. Now, mathematically, that kilogram meter per second squared is called a Newton. That's a force. It's a type of force that replaces kilogram meters per second squared. Now, because pressure is force applied over an area, we divide that by a 1 meter by 1 meter box, we get essentially 100,000 newtons per meter squared. Now, a Newton per meter squared is our Pascal, and 100,000 is the standard atmospheric pressure of on Earth. Now, 100,000 is not a pretty convenient unit, so we've managed to find a convenient exchange and exchange 100,000 pascals being equivalent to 1 bar. Now, bar is one of the 2 standard pressure units that we will use. Say 1 barometric unit. So if they at 1 bar, it's saying 100,000 pascals. Now, these guys are metric, but it's not the SIs. But so that means we could have a millibar, a kilobar, a microbar, all that stuff. We seem to be out of time. We'll continue with ATM and all that on Friday, assuming we don't have another surprise holiday that I totally spazzed on. In the meantime, thank you for your time. I will see you